Hello everybody, welcome back. Today we're going to look at 1.4 surface areas of right pyramids and right cones. So you may recall doing surface areas in previous grades where we looked at nets and you calculated the area of each of the faces. Well, we're going to do a similar thing here, but we're going to work with right pyramids and right cones. So first thing we're going to do is determine what a right cone and right pyramid is. So a right pyramid is a three-dimensional object that has rectangular faces and a base that is a polygon. So the base can be like a triangle, a square, a rectangle, a pentagon, and so on. The shape of the base determines the name of the pyramid. So a triangular face meeting at the point is called the apex, as you see here. All right, so there's all your faces. So we have the front, the back, and the two sides, the red and the other side here on the left. And the height of the pyramid goes from the apex right down to the base in the center of the base. All right, and that's that distance there. So that creates an inside triangle, which we're going to use. So I'll use those terms when we're speaking in class, okay? And when the base of a right pyramid is a regular polygon, the triangular faces are congruent. So therefore, if that's the case, then the slant height of the right pyramid is the height of the triangular face. So the slant height is the height, okay, of the triangle, if we were to flatten it out, I guess. So there's a regular tetrahedron. A tetrahedron is basically a right pyramid, a pyramid that has four congruent faces. So the front, the side, the back, and the bottom, if you wish. A right square pyramid has a square base, and the four triangles that make up all of the faces, they are called, they're going to be your faces, and they'll all be congruent. They're all the same. And the same idea with the right pentagonal pyramid. The base is a pentagon, and all five of these faces are congruent, which means they have the same surface area or the same area. The surface area of a right pyramid is the sum of all the areas in the faces. So in a tetrahedron, there'd be four total, and you would just multiply. You'd just find it of one of the triangle faces and multiply it by 4. In the square pyramid, same thing. You would do all the faces, the four triangular faces, multiply by 4, and then you would add the base, the square base, so just length times width, and so on. Once you get into the any polygons that are 5 or more, it gets a little more difficult to calculate the area of the base, but it can be done. Let's look at example 1. It says determine the surface area of a rectangular tetrahedron given its slant height. So the diagram's given. It has a slant height of 7.8 and a base of 9. So therefore I can just find the area of the triangular face, which is 1/2 the base times the height. I substitute 9 in for the base, 7.8 in for the height, which is slant height, because if we were to flatten this and create the net, multiply the two numbers together, divide by 2, or multiply by 1/2, and I get 35.1 centimeters squared. It's exactly that, so I didn't round yet. And since the surface area of a tetrahedron has 4 faces, I multiply the 4 by each face. So 4 times the area of the triangular face, so it's 4 times 35.1 centimeters squared, and I get 140.4 centimeters. And it's set to the nearest square centimeter, so therefore I round my final answer to 140. And that's it. All right, for tetrahedrons. And again, if you don't have the slant height, then it's a little more difficult. If you had the height going from the apex to the center right here, there'd be more calculations involved, and we're going to look at one like that in one of the other examples. Not with a tetrahedron, but with one of the other three-dimensional shapes that we have. Okay, you can do this one here. It's done the exact same way, only this time we have meters. Remember, you make sure the units are the same for all your lengths, right? If they're not, one has to be converted. So if this was centimeters and that's meters, you have to change one of the two. And since it was looking for square meters, they both have to be meters. This one was fine, but I'm just letting if that scenario does occur. Next, we'll scroll down to page 16. Which is the example 2. It says determine the surface area of a right rectangular pyramid. So in this case, there's going to be four faces, and then we'll say one base. Okay, so that we have four triangular faces and one base. We got the base dimensions at 8 by 10, and we have the height of 16. So the height is from E down to F in the center of the rectangular base, right? This is not the slant height. Slant height needs to be calculated. Okay, so in order to calculate the slant height, you'll notice what we've done is we've taken out the triangle, the two-dimensional triangle EFH. It's right here. So the blue one you see right here. This creates a right angle triangle. So now what we need to do is we need to use the Pythagorean theorem in order to calculate the slant height. The value from E to H will be the slant height, which we will then use to help calculate the area of each face. All right? So since it's a rectangular base, ED and C, so triangle EDC, will be equivalent to EAB. All right? If it's difficult to see, you find it difficult to see this in 3 dimensions, you'll have to draw the net. I'm not drawing the net at this point. You guys know how to draw the net, so that's when you take it and you flatten it out. If that helps you see it, you can do that. Maybe I'll do that in class just to give you an idea of what that actually looks like. But you've done nets in previous years. So I use Pythagorean theorem. So the hypotenuse is length E to H. I square that. That's equal to EF squared, which is 16 squared, and FH plus FH squared, which is 4 squared. So 16 squared, 256, plus 4 squared is 16. Then I add the two numbers together. I get 272, and then I take the square root of both sides, and I get the square root of 272. There is no need to, at this point, to find that value. Like, you don't need to take the square root of 272. It's not necessary. So just leave it as 272, square root of 272. So once we have calculated the distance from E to H, which is right here, you can see is the actual slant height in your diagram. Now we can find the area of that face. So that area of that triangle is going to be EDC, which is 1/2, because we know it's a triangle, 1/2 the base. Base is 10, distance D to C, multiplied by the height, which is the slant height in here in the diagram. The height, when you use area equals 1/2 the base times the height, is the slant height of a 3-dimensional object, right? So we plug that in, and we get 1/2 times 10, which is 5. So it's 5 square root 272 feet squared. You don't have to get that decimal. We can just do that at the very end. So it's easier just to take this with you. And remember, EDC is the same or congruent to triangle EAB. EAB is in the back, so E down to A to B. That triangle in the back, it would be congruent to the front. We'll say EDC, triangle EDC, because the front and the back would be equivalent, congruent, so they're equal. So that's why I have that here. So you can double that, or I'll show you what I did at the end when I'm finished. Now you got to do the exact same thing for the side with 8 feet. All right. So remember, 8 feet, because this side was 10, that's going to give you 5 here from F to G. So that's where the 5 feet comes into play. The height of to the apex of the center is 16. So EF, that would be the same there, obviously. So we do the exact same thing again with the Pythagorean theorem, only this time using 5 instead of 4, because it's a little wider here, right? Okay, the base of the triangle. So we get, we just work it out and we get the square root of 281, slightly larger. So this area of the ECB, so this left, or I guess the way, whatever you're looking at, the right hand side, so ECB, I say the side face here, that's going to be equal to 1/2 of 8 multiplied by the square root of 281. So it's going to be 4 root 281. There's no need to get a decimal here, just leave it. We want it to be exact. And it's congruent to triangle EDA, which is the opposite side, EDA, this triangle here, this face as well. and that gives you the 4 root 281, right? Because these are slightly smaller, the side ones, and that's why the value is going to be a little bit smaller. And then the base is a rectangle, so it's just length times width, so DC times CB, so it's 10 times 8, which is 80 feet squared. To get the surface area, you add up all 5 faces, I guess, so it's the 4 faces that are all triangles. Remember, front, back, side, side, and then the base is 80. And when I add those all together, my calculator gives me back. So once you've added up the 4 faces plus the base, so the 5 measurements, these are all feet squared. You get a surface area of 379.0286619, and if you look up, it says the nearest square foot, so the decimal 0 leaves it at 379. Answer with a complete sentence. The surface area of the pyramid is approximately 379 square feet. All right, so a little more meat to that one. You're doing 4 calculations. You're finding the area of the front and back face because it's a rectangle, the 2 sides, which are equivalent, and then the base. So the 3 calculations, add the 5 values up, the front, the back, the 2 sides, and the base. You can put your units at the end and then weigh around your final answer. Okay. The next one here, you can work this one on your own. It's done the same way, has the dimensions, the height, so you can look at the diagram above and your answer is going to be approximately 108 meters squared. That one, the first one was feet squared, the bottom one here is meters squared. Okay, and you give that one a try. In the next video, we'll look at example 3, determining the surface area of a right cone. Thank you, everybody, and we'll see you in the next video.